Welcome to our greetings. Welcome to our hands-on developer workshop. Thanks for joining us today. I'm Andrew Brown, Director of Product Growth here at ScyllaDB, and I'm joined by Piotr Sarna, the architect and developer of our native Rust driver, along with Felipe Cardenete Mendez, a solutions architect here at ScyllaDB, and the author of the sample app that we'll be using today. Our agenda today is broken into 4 parts. After a quick background on ScyllaDB, Piotr will provide us with some background on the design and architecture of the new Rust driver. And next, Felipe will demonstrate 3 small programs that show how to connect a ScyllaDB cluster, load data, and run queries in Rust with a few tips and best practices thrown in. Finally, Piotr will walk through tools for profiling and optimizing the performance of your Rust applications. By the end of the workshop, you'll have a good understanding of the Rust driver for ScyllaDB, how to install and work with ScyllaDB in the sample application, and finally, how to do performance profiling against your Rust apps. So before we get started, here are some instructions on how you can install the sample application and ScyllaDB. Clone the repo is shown here, and you'll be set up with ScyllaDB, the Rust driver, and the sample application. You'll need Docker to run the image, and pretty sure that most of you have Docker, but if you need it, go ahead and install that before you clone the repo. And finally, please join our Rust driver channel on our user Slack to get help with any issues and to provide feedback and suggestions on our approach to Rust. So a bit of background. Rust and ScyllaDB really combine to help developers write safe, reliable applications that run at extremely low latency on high availability distributed systems. What makes ScyllaDB uniquely suited as a database for Rust applications is its shard per core architecture and asynchronous non-blocking runtime. This is especially true for the types of low latency distributed applications that many developers are building, or in some cases rebuilding in Rust. So this architecture really lets ScyllaDB make full use of powerful modern hardware, giving it impressive scaling and performance characteristics capable of handling 1 billion operations per second, with P99 latency measured in single-digit milliseconds, with some of our users running clusters over 1,000 nodes. Today, we have a number of users who are actually rewriting critical streaming applications from Python over to Rust for the added performance and safety that it provides. If you're interested in learning more about the architecture, we have many tech talks and white papers on ScyllaDB's architecture that are all available on our website. So now let's get started. I'm going to hand it over to Felipe, and Felipe has a question that he would like to ask everybody before we dig in. So over to you, Felipe.
Thank you very much, Andrew. So the first poll that we have today is, how proficient are you with the Rust language? And the options we have, well, Rust is my primary programming language. Building production, you are already in the state of building production application, but it's not yet your main programming language. You are already using advanced features. I like this one. Like Felipe, I am learning. Yes, truth be told, thank you for putting that option over here. But yes, I am a novice Rust developer, so I am likely the less capable in class. And the last option we have, it's on my list to learn. So I can see we have a lot of people voting. Thank you very much for your feedback, people. And well, let's move forward and let's switch back to Sarna, who is our Rust driver developer, and he's here as our principal engineer. Sarna?
Hi everyone. Let me start with a short introduction on why Scylla and Async Rust are a great fit for each other. First of all, Scylla is, as Andrew already mentioned, it's self-designed and used for low latency and high concurrency workloads. It's built on top of C*, which you might heard of already, a modern asynchronous framework, similar in many ways to Rust Tokio, but based on a shared nothing model. Caesar comes with its own task and IO schedulers, custom memory management, and so on, and can be considered almost an operating system, actually. Scylla Rust driver that you're going to learn about in a minute is a bridge between Scylla's performance and asynchronous Rust. Together, they make it possible to write applications with high concurrency and strict latency guarantees. That covers Internet of Things applications that collect data from thousands of sensors, crypto nodes capable of serving multiple transactions at the same time, online chats, video games, many other potential use cases. Both Scylla and the Rust async ecosystem come with built-in observability tools, so metrics, statistics, histograms, traces, and more, which all help identify bottlenecks, get rid of some performance or latency issues. And last but not least, both Rust and Scylla adhere to the principles of green software engineering, if somebody's into that. The language itself, Rust, is on par with C and assembly in terms of power usage compared to other languages, and Scylla as a database also utilizes as much out of its resources as possible. That applies to CPU, memory, disks, network, and so on. And Scylla scales very well both horizontally and vertically, which means that you need less nodes to handle the same load as other databases would need. And that translates to less power consumption. Now about the driver. The idea to implement a new NewSQL Rust driver emerged during an internal hackathon at ScyllaDB over 2 years ago already. The Rust ecosystem already had a few drivers available, but none of them really fit our needs for a multitude of reasons. Unsatisfying performance, known bugs, etc. One of the options we had ready to use was CDRS, which now looks discontinued and forked as CDRS Tokio, by the way, which is coded in pure Rust, but it had a bunch of performance issues. First of all, secondly, it wasn't asynchronous and had a few bad known bugs. The other option was Cassandra CPP, which is based on the C++ driver. Then the project simply provides a thin Rust interface and binds it to the C++ core, which is not what we wanted. We wanted the safety of Rust. Thus, we decided to use our experience with existing drivers and carefully plan a new open source Rust driver written natively in Rust from scratch, and with very specific goals in mind. First of all, we wanted to be fully asynchronous. Then it should support token awareness and shard awareness, which is a Scylla specific optimization that lets you use CPU cores more efficiently. And it should be fast. It should produce as little overhead as possible, be easy to extend. Based on these ideas, we started coding Scylla Rust driver. Now, asynchronous Rust is based on a rather unique approach, namely a future promise model, but a specific flavor of it in which a future represents the computation itself, not just a result of a task that gets executed in the background as often happens in other languages. In async Rust, nothing is implicitly started in the background, and instead it's the programmer's responsibility to advance the state of asynchronous computations. And in order to do that, a runtime is customarily used. A runtime includes the capabilities of a scheduler, event loop, reactor, and so on. That's how this thing is called in many other languages. And due to async Rust design, runtime is not part of the language as it is, for instance, in Go, but instead there are multiple runtimes to choose from, or you can even write your own. And we picked Tokio. Tokio is pretty much a standard choice due to its very active development community, lots of features, and general ease of use. And side note, it would be perfect for us to write our driver in a runtime agnostic way without relying on any particular runtime, but we decided that the ecosystem is not yet ready for it. There are tons of important bits that are present in Tokio, like good TCP utils, timers, and other things that are not easy to code in a generic way, at least right now in Rust. Now let me hand over to Felipe and see some actual code.
Thanks, Sarna. All right, let's get our hands dirty a little bit. But before we do so, let me provide you a bit of context over what we are going to do and see next. So we are going to demonstrate 3 different and small Rust programs, which will cover best practices around how to connect and fully utilize your ScyllaDB cluster. Our sample code is a simple application that simulates 100 IoT devices recording temperature samples against the database every 300 seconds or 5 minutes for a period of 3 days. It demonstrates an append-only time series type of use case. So the first program that we are going to see is called metric collector. This program, simply put, will create the necessary resource, key space, and table on the database and generate and write data to it. The second program is called metric reader, and it demonstrates how to efficiently perform full table scans against ScyllaDB. In that program, we will split the token ring in smaller chunks, and using the token function, along with the bypass cache SQL extension, we will count how many temperature records each device has. This program is a good example on how to efficiently perform analytics type of queries using the Rust driver, and simply put, it tries to apply similar principles as technologies such as Apache Spark or Presto employ when running ad hoc type of queries against the database. The third and last program is more of a simplistic one, but can be seen as a real-time example for reading data. In that program, as opposed to the previous one, we now know which IoT device we want to query. And by using some functions such as maximum, average, and minimum, we can efficiently retrieve statistics for a single device comprising a given period of time. One last heads up before we get started, guys. As it was pointed out in your initial poll, I am still a beginner Rust developer, and these specific programs were initially written for me to learn the Rust language. I'm still doing my first steps, and I would love to hear your feedback should I have missed some Rust-specific best practice. Therefore, for the actual demonstration part, we will cover the ScyllaDB Rust driver specifics more rather than Rust language specifics. Okay, all right. So let me fire up my terminal. In order to save us some time, I have already brought up our working environment, which let me run it, Docker PS. So it basically contains 3 Scylla nodes, our cluster, and our Rust application container. Okay, so to make things easier, what you want to do after you start everything is to check the logs of the Rust app container. All right, and you can do that running docker compose logs -f Rust app. And what you want to see is the message saying that ScyllaDB is up and available, and that you are ready to go. So once you get this message, there are 2 things that I want you to do. First, open a new terminal, and I have already opened it down below here. And within that new terminal, let's connect to one of our Scylla nodes. I'm going to choose node 01 and fire up SQL S8. Okay. And from here, what we are going to do is to run the describe schema command, which basically has shown us nothing as its output, therefore showing that the cluster has no user data, which is okay. This is where we want to be at without anything on the cluster. All right, so keep this shell open and let's move to the previous shell. We can exit that pressing Ctrl+C. And what we are going to do now, we are going to log in to our our Rust application container. And let's run our first program. So our first program, remember, it's going to create our research and start ingesting data to the database. So, and that's it. I mean, that quick. We have run 86,402 queries against ScyllaDB and wrote our data. So at the end of every program, remember we have 3 simple programs that we're going to see, but at the end of every program, the metrics, the client-side metrics are going to be shown on the screen, which you can use to gain some insights of its overall performance. Before we actually get to inspecting its code, another word of caution. Do note that our entire infrastructure is being run on a consumer-grade laptop, which, in my view, only makes these results more impressive. Okay, so we have run fairly quickly over 86,000 queries. Okay. So remember that shell which we had opened before to connect to CQLS8? Well, let's go back to it fairly quickly. Let's run the describe schema command again. And now it's showing us that the resources that we required are created. So we have our key space, our table, but do we actually have some data on top of this table? Let's take a look. So let's run a select everything and limit to 1 because we are only interested in 1 record. So yes, we have data in this table. Okay. Now that we are past the first program, let's examine its code. So I'm going to open VI and we want the metric collector source main.rust. All right. So before we deep dive into the actual Rust driver specifics, I want to briefly speak about the parallel constant you see over there. For this specific example, since we are ingesting a lot of data at once, we are also defining a max concurrency of 2048 in-flight queries. Okay. In general, when you are designing your application, it's commonly a good practice to ensure that you have a mechanism to control the concurrency to avoid overwhelming the database. Should this not be possible, ScyllaDB has a configuration option that's capable of shedding requests once it hits a concurrency limit, or if you feel like you are hitting a hard limit, you can scale out your cluster and or review your access patterns data modeling. All right. Okay, so the first thing that our program does is to parse the command line arguments that were sent when we invoke the program. So one of those command line arguments is the host, which by default is localhost. And we also need to specify the data center, which by default is data center 1, but you can change it to whatever you want. So one important mention about the contact point and how the driver behaves. So once the driver connects to a single node in the cluster, the first thing that it's going to do is it will discover the whole cluster topology, and it will automatically open connections to other nodes that are part of the cluster automatically. So one question that we often receive is, how many nodes, how many contact points do I need to specify in my application? The typical recommendation is for you to have at least one node from a different rack and data center as contact point for your application. For example, in a minimal production workload, you will typically have a deployment of a 3-node cluster where each node is located in a different availability zone. Therefore, it makes sense for us to specify all 3 nodes as our contact points, since the failure of a single node won't prevent new application clients from connecting to the cluster. Okay, let's just scroll down. The next step that our code does is basically to define the key space and table that we are going to use and write throughout our application. We chose IoT for the key space name and table and device for the table name, respectively. Okay, what we do next? We basically start a cluster session. So you can see over here, initiate a cluster section. But before we start the session over here, before we do that, we specify the loading balancing policy that we are going to use, which basically tells the driver which nodes it should contact for your queries. Okay, so one of the things that we are using over here is the DC-aware round-robin policy, which means that the driver will ensure that your queries are only being sent to nodes in the same data center as we specified earlier when we first called the program. This is helpful when you have a multi-DC or multi-region solution and want to avoid your application from sending queries to a different location. In fact, as a general good practice, you will typically want to collocate your application close to the database for latency reasons. Okay, so what do we do next? We then add the token-aware round-robin policy on top of the DC-aware policy to ensure that our queries are being sent to nodes that are actual replicas of the data we are writing to or reading from. For example, you may have a 6-node cluster and a replication factor of 3, which means that only 3 copies of your data will reside across different nodes of your cluster. With token awareness, reads and writes to your data will go directly to the nodes which are also replicas. Therefore, this is an additional tuning we do to avoid network round trips and reduce on latency. About load balancing policies still, it's also worth to mention that there are other load balancing policies available within the driver. And since one solution never fits all, you can even create a policy of your own to decide how the driver should balance your queries. For our examples over here, we are using DC-aware and token-aware loading balancing policies. Okay. All right. So we then specify the session and we create a session to the cluster. Some interesting options that we are specifying over here: the loading balancing policy that we have just spoken about, the compression algorithm. We are using LZ4, but we also support Snappy, and we also specify the credentials, username and password to use when connecting to the cluster. Okay. For those of you who are running ScyllaCloud, and if you would like to run this example in ScyllaCloud, for instance, what you have to do, simply put, you are going to simply override the username and password with the ones that have been created for your cluster. And you are simply going to change the contact point in order to connect to ScyllaCloud. Okay, so once we connect to the cluster, the first step that we need to do, since remember our database was empty, it had nothing created. So the first step is, of course, for us to create our key space and our table. There's one important topic that that I want to cover before we get to the part when we start ingesting data, etc. Every time you are going to do some kind of schema change programmatically, you will typically want to wait for the cluster to get in what we call a schema agreement. That is, all the nodes in your cluster recognize the change that we did before we proceed. And the Rust driver similarly has a function that we can call in order to check. And we can also specify for how much time we are going to wait before proceeding with our processing. In this example, we are telling the driver to wait for up to 5 seconds. Okay, so after we are past the key spacing table creation steps, the next steps that we have is to prepare or insert a statement. One word of caution, keep in mind that only prepared statements use token-aware load balancing, okay? And it's highly recommended that you use prepared statements for performance and latency reasons, okay? So we then tell the driver that the queries we are sending for this statement that we have just prepared over here, they need to have a consistency level of local quorum, which means that a majority of replicas must acknowledge the operation before we consider it successful. Finally, what we do next, we set a retry policy, which basically tells the driver to retry queries that could have failed if it believes that there's a high chance of them completing. So this line here is only for educational purposes, because this is actually the default. Similarly, as the loading balancing policy, there is another policy that you can use, which is called fall through retry policy, and which effectively never retries. Or you can also create a retry policy of your own. For example, you may have an analytics type of use case where you don't want you don't want to retry queries which had failed, whereas you want your real-time use case queries to always succeed. So this is a naive example situation on which you may want to override the driver's default retry policy. Okay, so the next steps, for those of you who are familiar with the Rust language, they're most simplistic for us to understand. So we start ingesting our data in a loop fashion, as you can see over here. And we create a number of semaphores as we specified in your concurrency in the beginning, as we have seen in the beginning of the program. And then we do Tokio task. We call actually a Tokio task calling the execute method on the prepared statements after we have bound the parameters that we want. And this is how we ingest data to the database. So once we finish writing to the database, we wait for our in-flight request to finish, and we finally print out the driver metrics to the screen. So once again, this is a very nice driver feature that you will want to integrate on your monitoring metrics, as it will allow you to quickly have live insights on how your application is performing with ScyllaDB. All right, so now that we have seen the basics of our first program, how to properly connect to a ScyllaDB cluster and how to execute statements against it, let's move back to our Rust application container and let's run our second program. Let me paste. Yep. So as we have seen before, our second program is very similar to the first one, but instead of writing data to the cluster, it will efficiently perform what we call a full table scan and count how many metrics per device have been collected. So before we get into the part where we inspected the code, to efficiently perform a full table scan, we need to remember the way data is distributed across a ScyllaDB cluster. So First, when we are modeling our data during table creation, we needed to specify what's going to be our partition key. So once we write to the table, the partition key is hashed using the murmur tree algorithm, and in return, we get a token. The token will determine which node in the cluster is responsible for holding that information. Depending on our key space replication factor, additional nodes will also hold the data for the given partition as replicas, which is how ScyllaDB achieves high availability. Therefore, the data from our first program was spread across our cluster token ring. Okay, so let's go back and see the code of our second program. So I'm going to open the metric reader, search, and call our main function. Once again, we parse the arguments, and then we set up the key space table, pretty much the same as we have already seen in the first program. So what the second program does, simply put, is to split our token ring. And our token ring is basically -2 to the power of 63 minus 1 up to 2 to the power of 63 minus 1. So as you can imagine, it's a very big number. And then we get that big number and we break it down into smaller chunks. Okay. What we do next basically is this is basically hard coded over here, but we tell our program how many nodes we have, how many cores per node do we have, and we specify the parallelism on which we are going to, or the concurrency that we are going to run against queries against the cluster. So basically parallelism is the number of nodes times the cores per node times 3, because you want to ensure that you have enough concurrency to have all the CPUs busy enough to always to get the best performance that we have. Okay, so once we get that parallelism, what we do next? We multiply this by a factor of x, which in our example, we are using 1,000, but it will vary per use case, okay? So this is basically how many queries we are going to send in total. And what we do next is basically we divide the total number of tokens that we have by the parallelism that we have determined before. And this is basically going to give us the number of iterations that our programs needs to run in order to perform a full table scan. Okay, so what do we do next? We then move on to the prepare statement section, where here, basically, what we are doing is we are using the token function where we are going to specify, we are going to bind the parameters to specify the token range that each query needs to run. And if you pay attention closely, at the end of the select statement, we are adding the bypass cache at the end of the select statement. So the bypass cache operand is something that you will always want to have when running such types of full table scans. What it does, simply put, is to tell the database not to populate its cache with the data it reads. Therefore, our reads are going to disk. And yep, of course, this has a latency penalty. But generally speaking, when you have, let's say, analytics and real-time use case running on top of a single ScyllaDB cluster altogether, you typically don't want your analytics use case to pollute your cache, as this may cause increased latencies over your real-time workload. So that's why we are adding the bypass cache over here. Okay, so what our program does next, simply put, is once again, we are going to iterate through the data that we have discovered into the beginning. And we are going to send several queries in parallel in the very same way as we have written. And every time a query finds a device, we are going to print in the screen how many rows for this device have been shown. Okay, and then similarly as the first program, we wait the in-flight queries to finish, and then we show the metrics again to back to the screen. And if we take a look over here at our output, you can see that we have around 80,001 queries, and our P99.9 latency percentile was 7 milliseconds. Remember, guys, this is running in a consumer grade laptop. This is very impressive. So it's very, very quick. All right. So let's execute our third and final program, which is the one which is more geared towards a real-time use case. So, oops, I added a hash sign over here. Yep. So this one is simple. Simply put, in this one, as opposed to the previous one, we now know what is the partition key that we want to query. And we are specifying a range of time over which we want to retrieve data. And then on top of the data set that's retrieved back to us, we run the max, minimum, and average queries on top of it, so we can know how temperature varied across this specific time frame. Okay, just a heads up, the way this program generates temperatures is pretty much random. So don't worry if you see some weird values, such as the maximum was 49 degrees, but the minimum was minus 39. So it was simply written for this purpose, okay? So let's quickly take a look over its code. Oops, UUAD Finder. And once again, we parse the arguments that we had sent into the command line. And this is, well, as I have said, I am a beginner Rust program. And typically, one of the things that we typically see when people start to learn a programming language or try to integrate it with a new driver or another solution is that we need to learn how to reconvert dates properly. And if you need some assistance with that, this is how you actually do it. So in the end, basically, you are going to convert or input dates to a duration, okay? What we do next, we basically prepare the statements after we have connected to the cluster. So select max, minimum, average from the table where the device is the one we received in the command line, and the timestamps are bound parameters. We execute those queries, show the results back to the screen, and then once again, we print the metrics back to the screen. Okay, and this is basically the quick overview of our 3 programs, and it was nice because we covered some very good best practices. And this brings us to the end of our coding session. I hope you have enjoyed. And again, should you have any feedback or suggestion, feel free to reach me out. And before we hand over back to Piotr, let's quickly take another poll. So what database do you use or are planning to use for Rust applications? So I can see we have many databases over here. I'm not going to speak about them. And I can see once again, a lot of people are responding. Thank you very much for taking your time and giving us the feedback. So Piotr, back to you. Thanks.
Hi again. Let's take a deeper technical dive into profiling now. Profiling as in investigating performance problems and looking for bottlenecks in your Rust projects. So overview of the first tool. A few weeks ago, Tokio console was released in its first early version. And with Tokio console, you can browse which tasks are currently active, which resources like semaphores or queues or timers are taken, used, which are free, what are their parameters. And all in all, it gives you a very nice insight into how your async code works underneath. In order to set it up in your project, it's quite easy. You just need to add an appropriate entry in your dependencies in your cargo tom file, and then initialize the console subscriber with a single line that you add to the code. Now, since at least at the time of writing these slides, support for the console was experimental, and I think it still is. You also need to specify an unstable Tokio configuration variable during compilation in order to enable Tokio console. So now time for a quick demo. Let's set it up. First of all, ask for changing the actual source code. This is the only line that you need to add to initialize the console subscriber, which will start sending data to Tokio console once the program runs. I just edited and added this single line to one of Felipe's programs. Now we can run this program. I compiled it in debug version so that it's slower and it doesn't end in sub-second time, so we can have some time to actually see the results of Tokio console. So here it is. It might look a little cryptic to you, but it's fine. You can get used to it. There are two main tabs in Tokio console. The first one shows you which tasks are currently running. Task is a well, kind of a fiber of execution that is executed by Tokio, along with various stats on their state. These results are live, so you can pretty much browse what happens in your program right now. The second tab shows resources. That's a very nice touch, but they also show it. Resources are pretty much every utility that you can imagine. So semaphores, timers, channels for communicating between fibers. All of it is right here. So if you have a potential bottleneck, for instance, a semaphore or a mutex that's heavily contended, it's very likely that you're going to see it right here, that it's that your program spends too much time on this particular semaphore. Right, so that's a very neat tool for looking for bottlenecks. Tool number two. So since the Rust ecosystem is all about programmers' ergonomics, it of course also has a one-liner way of generating flame graphs. And a flame graph is, well, it was created and popularized by Brent and Greg. It's a very neat tool for visualizing stack traces, along with how much CPU time each frame took for the execution of this frame. And in order to generate a flame graph out of your program's run, you can just install Cargo Flame Graph, which is yet another cargo utility, and then just run it as simply call Cargo Flame Graph and then path to your project, and then it just works. Now, just to show you how simple it is, instead of cargo run, you can just type Cargo Flame Graph and run it. Now what you see here right now is recompilation, because there are some specific compiler options that are used when generating a flame graphs. Namely, you need to enable debug symbols and turn off some potential optimization that hurt debugging. So we're not going to wait for that. I have a flame graph generated beforehand. That's how it looks like. It's full of details that I don't expect you to follow right now because there are thousands of frames here. What's very nice is that this whole flame graph is interactive. So it's if you see that some particular flame is well suspicious and you would like to zoom on it and check what it is, you can just click on it, and now we can figure out what actually happens here. This is actually full of Tokio details, so it's also hard to follow. But if you're looking for bottlenecks, then it's a really nice tool, because if some particular operation is going to take a long time, it's going to be very wide on this flame graph, and it will be easy to figure out why it happens so often or why it takes so much time. Right. Now on Linux, flame graph is actually just a really nice and attractive and interactive output based on another tool, which is called Perth. Perth is a very powerful profiler with in-kernel support. It's full of capabilities. So if for any reason you decide that flame graphs are not enough for you, you can well, quite easily use Perth directly on a Rust executable, because Rust just compiles to an ELF and executable that you can browse on Linux. A few hints first. If you run Perth but you keep seeing unknown symbols or errors, there are a few things you can try. First of all, remember that debug symbols are normally not included in the binaries that you compile for a release mode. These binaries are instead stripped in order to make the final binary smaller. So set the debug equals true in your cargo profile in order to keep the symbols. And also LTO, which stands for link time optimization, should better be turned off for a round of debugging if you still see issues, because while it can considerably speed up the execution time of your project when you compile with link time optimization, it can also mess up the debug symbols, making it next to impossible to decipher stack traces from frames, and the stack traces will not be that useful. And finally, Linux is quite protective of your safety by default, which is good. But yeah, it doesn't let non-root users speak too much into kernel symbols and receiving all the perf events. So if you want to be able to access these symbols without being a super user, you can turn these protections off, either just for a while or for good. So let's also see some perf result as well. In order to run perf, first of all, funny thing, if you run cargo flame graph, it will actually leave a side effect, a perf.data file on Linux, and that's exactly the perf output. It's a nice touch that cargo flame graph doesn't remove that, because we can also check it out with perf. But let's run perf directly. I'm going to use -G option, which generates a full graph of calls. And now let's use the path to one of our binaries. Oh, pardon me. You need to call a command in perf. So perf record is going to record all the traces. We don't need to wait for it all, so we can just break it in the middle. But yeah, now we have a perf.data file, and in order to see that file, it's enough if you just call perf report add -G if you want to see a fuller graph. And yeah, here it is. It's also quite cryptic at the moment, because most of the things you see here are actually Tokio symbols, which is good because it suggests that the app itself isn't a bottleneck, but instead it just uses Tokio as it should be to communicate with the database in a synchronous way. You can also dive a little deeper and try to see if you need some more details, what took which amount of time, how much processor time. Right, and Perth is perhaps the most advanced tool. It's full of really nice options that I'm not going to cover in this talk because it will be a few separate workshops for covering Perth only. But that's how you can use it in the Rust project. So thanks, folks. That's everything on profiling. Let me give the mic back to Andrew, since I think it's time for QA.
Yes, thank you, Piotr. Thank you, Felipe. That was great. Getting lots of good questions in terms of support and getting things working, and asking whether this will be available as a recording afterwards so that you can follow up. Yes, we'll make this available. Of course, please sign up for the Slack so that we can kind of collect your ongoing feedback and provide ongoing support as you get more familiar with code and take it in new directions. I have one question here, which is, I think this is for you, Piotr. What is the release status of the Rust driver, and what does the roadmap look like for the Rust driver at ScyllaDB?
Right. So, as a matter of fact, I just released another pod version today because we had some new fixes that arrived, and right now the driver is at 0.4.2. And the latest release covers some load balancing fixes that would and also expands the capabilities for us to gather debug logs in case something doesn't work. But in general, well, it's on its best way to release 1.something, which would be an official stable release with a stable API and so on, because people already started using the driver in production. So that's the best testing that we could actually hope for, aside from our own tests and benchmarks. So yeah, that's the summary of the status. It's going really well. We have a release every 2 or 3 weeks.
And any plans to add new features to the driver?
Well, constantly. You can browse our issue tracker on GitHub. There are some feature requests right there. By the way, if someone wants to contribute, then you're welcome to join. And we've already had several nice open source contributions. So yeah, our plans and our short-term roadmap is pretty much summed up on this issue tracker. We have a few plans with rewriting the load balancing, the way you can define your own load balancing policies to make it more user-friendly. Then maybe we will add execution profiles, which is something that other drivers have and we don't have yet. So yeah, that's a couple of things that we still have done.
Okay, and here's a question. Is the Rust driver going to be called from other drivers? And the example here is Golang.
Well, it is already, if you mean using the Rust driver as a core implementation for other languages, then C++ is already work in progress. Python is next. Go would be nice, although I find it a little tougher when I think about it, at least because Go already comes with kind of an async reactor built into the language itself, so it would probably be a little more challenging to just replace it. But sure, why not? Ultimately, it would be best to unify all possible drivers that use CQL to use our Rust driver underneath.
Okay, great. And then we have one question. What's the timeline for releasing a production-ready version of the driver?
We don't really have one. Right now, we're at 0.04, which means that we still don't promise that we are not doing any changes that break compatibility, because we would still prefer to have some time for gathering user experience. And so I don't really have any hard deadline for a 1.0 release. Well, it would be nice to see it this year, but it's just a wild guess on my end right now, because we still both have lots of benchmarks and testing planned, as well as features.
Yeah, that's good. And I think the best place to track the progress of the Rust driver is, again, if you want to join the Slack, we have a dedicated channel just for the Rust driver. So if you get in there, you can continue to ask questions and get updates on the release roadmap. Well, great. I think that is all the questions that we have time for today. Actually, a couple of questions just came in. We'll follow up with those because they require slightly longer answer than we can provide here. But thank you, Piotr. Thank you, Felipe. Thank you for everybody joining today. And we look forward to continuing the conversation.